Imagine you're watching the evening news and the meteorologist warns about a fast-moving storm system racing across the Midwest. You look outside and the winds are calm, yet this storm is moving at an incredible speed. How is that possible? Why does the storm seem to have a mind of its own, traveling much faster than the winds you feel at the surface? The answer lies in the layers of the atmosphere above us, steering the storm like an invisible highway in the sky. One of the most incredible examples of this was the Midwest Derecho on June 29, 2012. This storm was not just another thunderstorm. It was a massive wind event that traveled over 700 miles in just 12 hours, causing destructive damage and power outages for millions of people. But what made it so fast? Why did it take the path that it did? And most importantly, why do meteorologists predict where storms like this will go? In this video, we're going to explore how storm motion is influenced by different layers of the atmosphere, how we calculate something called the mean wind, and why factors like upper level winds and outflow boundaries can accelerate storms beyond what the mean wind alone predicts. By the end of this breakdown, you'll have a deeper understanding of how meteorologists track and forecast storm motion. So let's dive in. When tracking storms, looking at surface winds alone won't give us the full picture. A common misconception is that storms move with surface winds, but that is rarely the case. Instead, storms are steered by winds at multiple heights in the atmosphere, creating an overall movement that is often very different from what we feel at the ground. Meteorologists use a concept called the mean wind, which is the average wind speed and direction across multiple levels of the atmosphere. This helps us estimate the storm's overall movement much more accurately than simply looking at surface winds alone. Take a look at the skew-T diagram for Wilmington, Ohio. This was taken just behind the derecho that gives us a snapshot of the wind structure at different altitudes. At the very bottom, the orange represents surface winds, which are influenced by friction and terrain. As we go up, we see the red, brown, and blue wind vectors representing winds at 850 millibars, 700 millibars, and 500 millibars. Each of these layers play a role in guiding the storm. By combining the wind data from these layers, meteorologists calculated the mean wind vector, which provides a better estimation of storm motion. But how exactly do we calculate it? Let's go step by step. Now let's get into the actual math behind calculating mean wind. It may seem complicated at first, but once you understand the process, it becomes a valuable tool in forecasting storm motion. To start, we'll take the wind speed and direction at different atmospheric levels and break them into two components. The U component represents the east-west motion, while the V component represents the north-south motion. This step is necessary because wind direction is typically given in degrees, which does not directly tell us how much of the wind is moving in each direction. To calculate these components, we take the wind speed and multiply it by the sign of the wind direction for the U component. For the V component, we multiply the wind speed by the cosine of the wind direction. Since meteorologists measure wind direction from where it is coming, we apply a negative sign to both values to ensure proper orientation. For example, at the 850 millibar level, the wind is coming from 290 degrees at 30 knots. When we apply this method, we find that the U component is 28.19 knots, meaning most of the wind is pushing towards the east, and the V component is negative 10.26 knots, meaning there is also a smaller southward component. We repeat this process for the surface 700 millibar and 500 millibar levels, giving us U and V values for each layer. Next, we calculate the average U and V components by adding them together and dividing by the number of levels. This gives us the overall mean wind components that represent the collective influence of winds across the different layers. For this case, our final values are 29.74 knots for the U component and negative 9.43 knots for the V component. Now, we take those mean U and V components and convert them back into a single wind speed and direction. To find the wind speed, we take the square root of the sum of the squares of the U and V components. This gives us a total wind speed of 31.2 knots, or about 36 miles per hour. To determine the wind direction, we use the inverse tangent function, also known as arctangent or atan2. This function calculates the angle of the wind vector based on both the U and V components. We take the negative of the U component divided by the negative of the V component, which ensures the angle is placed in the correct quadrant of the 360-degree system. When we apply this calculation, we get a wind direction of 288 degrees or west-northwest. Now that we have the mean wind calculation, how does it compare to the actual movement of the Derecho? Now that we have calculated the mean wind, let's compare it to the actual motion of the Derecho. According to our calculations, the mean wind suggests the storm should have moved at approximately 36 miles per hour from a west-northwest direction. However, the Derecho moved much faster at nearly 75 miles per hour and slightly more southeast than the mean wind indicated. So why the difference? This is where we introduce the additional forces that modified the storm's speed and path. Momentum from upper level winds. The winds at 500 and 700 millibars were much stronger than those at the lower levels. These winds provided extra push, enhancing the forward motion of the Derecho beyond what the mean wind alone would suggest. Stronger upper level winds mean faster moving storms, and in this case, they contributed significantly to the Derecho's rapid movement. Cold pool dynamics and outflow boundaries. Cold pools from when rain-cooled air sinks and spreads out at the surface. This can create a powerful outflow boundary that reinforces storm motion. As the cold air surges outward, it forces warm, moist air ahead of the storm to rise rapidly, helping to maintain and even accelerate the storm. Mesoscale processes and local interactions. Finally, some small atmospheric interactions played a role in sustaining the storm speed. Subtle shifts in pressure gradients and interactions between the storm's inflow and outflow regions help to keep the Derecho moved rapidly. While the mean wind gives us the great estimate, those additional processes must be considered when forecasting storm motion. Now, let's take a closer look at how mid and upper level winds contributed to the storm's rapid acceleration. One of the biggest reasons the Derecho moved so fast was the influence of strong upper and mid-level winds. These winds acted as a guiding force, steering the storm along and increasing its speed. At 500 millibars, we see a powerful west-northwest flow that helped ventilate the storm, allowing it to sustain its strength. This level is crucial in Derecho events because it influences how much forward momentum the system retains over time. At 700 millibars, we see another strong west-northwest flow, reinforcing the motion of the Derecho. These mid-level winds played a key role in shaping the trajectory of the storm. Together, these winds created a conveyor belt effect, accelerating the storm and sustaining its momentum over hundreds of miles. However, upper-level winds were only part of the equation. Another crucial factor that contributed to the Derecho's rapid movement was cold pools and outflow boundaries. Let's explore their role next. Cold pools form when rain-cooled air descends and spreads outward along the surface. This creates outflow boundaries, which act like miniature cold fronts, reinforcing storm motion by providing additional lift and forward momentum. Looking at this dew point map, we can clearly see where these cold pools were forming. Lower dew points behind the Derecho indicated where the rain-cooled air was spreading outward, while higher dew points ahead of the storm show the warm, unstable air feeding into the system. The interaction between these air masses helped the Derecho maintain its forward speed and even accelerate in some areas. This is why forecasters closely monitor cold pools and outflow boundaries when tracking fast-moving storms. In essence, cold pools are another key force that contributed to storm motion. When combined with upper-level winds and mean wind calculations, they provide a much more complete picture of storm motion. Now that we have broken everything down, let's recap the key takeaways from this case study. Number 1, mean wind calculations provide a solid estimate of storm motion, but they do not tell the full story. Number 2, upper level winds at 500-700 millibars played a significant role in steering and accelerating the Derecho. Number 3, cold pools and outflow boundaries reinforced storm motion, helping sustain the Derecho's extreme speed. And lastly, meteorologists use a combination of mean wind analysis, upper-level wind observations, and mesoscale dynamics to improve storm forecasting. By understanding these influences, we can better predict and prepare for future Derechos and other extreme wind events. If you found this breakdown helpful, I'd love to hear your thoughts. Drop a comment below with your biggest takeaway. And if you enjoy deep dives into meteorology, make sure to like, subscribe, and hit the notification bell so you never miss a video. Thanks for watching, and stay weather aware.